Yeah, I should apologize right off the front from the title. A couple months ago when I had to submit something, it seemed like it fit, but after listening to the earlier talks the last few days, I realized it probably is very misleading. This talk has nothing to do with net booting or file system booting, or really not that much to do with booting at all. It's really about the core of our fault system, but you'll learn more about that. Uh-oh. I don't know how to work this. Well, there it goes. All right. So our approach or our perspective is a little different too than I think most of the presenters. We build CDPUs for instruments, for science instruments. So we're down in that really low level of these missions that actually collects the data and keeps the damn scientists happy that we heard about before. And our goal in our CDPUs is to build a system that is highly reliable, has a boot segment that's highly reliable, allows us to deal with any other problems that come up further downstream so that we can keep this instrument running even if there are unforeseen issues that come up, so that we can still produce data. And that's the driving design feature in the way we do this. So the key for our boot code is that it has to be able to allow us to reprogram the device. So we don't, in earlier missions, we would have a boot PROM that would allow us to do a minimal science mission. And for recent missions, we've given that up now. And the real purpose of the boot PROM is to make sure that we can rebuild using the resources we have available within the system. And maybe not the ones we originally intended to use, but whatever's on the system. And so this boot code is our key to recovering from some damaged or failed parts, depending on what's happened. So the flight software, the image that is running, could be rebuilt, redone on the ground, and reloaded into a different resource than was originally planned. We'll get to that a little bit later. So again, in the past, we typically used some sort of a processor with a boot PROM to do this job. For these missions, our recent missions, we've decided to build our own processor in an Actel, in an RTX 2000, using the Leon fault-tolerant code from Geisler Aeroflex. And so that gives us the opportunity to take advantage of some unique features of that. Or I'm the software developer, not the FPGA developer, so this may not be completely unique to these, but it's something that we can take advantage of here. By putting our processor or all of, everything into this one FPGA, all of our interfaces, and that coupling them with the IP core, there's also a feature of the Leon 3, the AHBROM, that allows you to put code into the FPGA. This advanced high-speed bus read-only memory, it's an optional configuration item that can be used with the Leon 3. Just as there are some limits. We're not going to put our full science mission in this FPGA. It would take up a lot more space, a lot more gates than they're willing to give us. So the FPGA developer and I sort of worked out a deal that okay, I could have a couple of % of the FPGA to put some code in, and that's the way it worked out. And it actually worked out quite well. It really didn't impact his margin much, but it gave us enough to work with. And again, this is just it's a feature that comes with the Leon 3 architecture. And so I won't go through the full details here. It's all documented very clearly in the GRIP documentation. The key thing for me as a software developer was that the code is built by my normal tools. There's nothing special about this piece of software. It's written in Spark Assembler. And we just compile it like any other piece of assembly code to put into the system, and then hand it off to the FPGA developer, and he just compiles it in, and it's now part of the system. He had to do some work to make that happen too, but that's his problem. So the design criteria for this boot code is that it not use any external, not make any assumptions about external resources. So it can't use the RAM, it can't use the NVRAM on the board. It has to come up and operate the FPGA, be operatable totally within the FPGA. And so one of the side effects of this, as well as giving us a robust platform for fault handling, it also gives us a nice test environment, because we can test our board, our CDPU board, before we put any of these devices on it. We don't need any RAM or any SRAM or any CRAM, any NVRAM to be able to bring up the board and check out all the interfaces. And I'll show you that in a minute. It also, this eliminates really the need for a PROM. So we really don't need that separate step, that highly reliable device, that non-reprogrammable device is now built into the FPGA. So it reduces the parts count and makes the board simpler. Just to give you, this is our CDPU board for MMS, for our fields experiment, the electric field experiment. And see, here's the Actel with the FPGA on it. These are all the memory devices, the CRAMs, the SRAMs. And so, as I'll go through, that when the board developer brings up each flight board and it has it populated, all the interface logic is put on, the Actel is put on, but these are not. They're left off, so we can test the board rather than putting on these expensive and difficult to work with parts. They can make sure that there aren't any other problems to avoid rework. If there's a problem with the board, it's a lot easier to stop at this point than it is to put these parts on it, to take them off or worry about them. It also, again, allows us to exercise the system really early in the development. So the typical board testing sequence is that we'll put everything on but the SRAM and CRAM, and then execute a board functional test using the AHBROM code. And again, I'll get into a little bit later as to what that provides. It's minimal, but it's enough to work with. And then we go through and, then we put the SRAM on, and then using the AHBROM code, this boot code, we can load code into the SRAM to allow us to do more elaborate testing. And eventually we put the CRAMs on, the non-volatile RAMs, and load our power on self-test, and eventually load our flight software in. And then we can do our full functional test on the board. The general philosophy of this boot code is, first of all, the keynote speaker was talking about, you spend a lot of time developing this code that you hope you never use. And the main job of the AHBROM code is to get through it and get on to the higher level code, pass things on to the power on self-test that's in the CRAM, which then passes code on to the RTEMS image that is also running out of the CRAM. So in the best case, you spend very little time in this code and never use any of it. And so the normal flow is to test the non-volatile RAM portion that contains the next step, the power on self-test in our case. If it's okay, you jump there and you're done. You never come back to this section again. If it's not, then we enter what we call FAILSAFE. That's the code within the FPGA that allows us to diagnose and to continue working and to rebuild. Also, if for some reason we don't want it to promote up the chain, either we're doing a test or we're doing some diagnostic where we don't want it to, we can, within the FPGA interprets the reset command and can pass flags into the flight software so that the AHBROM code can detect a flag that says don't promote to post, stay in the failsafe, stay within the FPGA, and wait for further commands. Otherwise, if a fault in the higher level system are running in the RTEMS image and certain faults occur, we'll jump directly into the failsafe and wait. Again, part of the FPGA design is to have a few commands that are parsed within the FPGA. Most commands are handled by the flight software, but a couple of them, the reset command is interpreted by the FPGA, resets the hardware, but it also passes an 8-bit field onto the flight software. A couple of those bits are used to either permit promotion to the power on self-test. Most of them are used in the higher level in the power on self-test to decide what boot image to use, and a lot of options. You got 8 bits to play with. You can make any decisions you want based on those. CRAM write enable is another one that is handled by the FPGA. That has to be done by an external command in our systems. The flight software is not permitted to write enable the CRAMs. We also, on MMS, there's an external, an asynchronous interrupt that comes from the processor upstream, the central instrument processor for the payload. And again, I'll get into a little later, but having a command come in while we're in the process of booting can be highly disruptive. And so the FPGA does allow us to do things like block certain commands while we're in the boot process. I'll talk a little more about that later. And the other commands are passed directly to the flight software through a non-maskable interrupt. This is just a block diagram of the AHBROM structure, and I'm going to show it to you for two different missions that we've developed it for. You'll see a lot of similarity. This is the field's MMS AHBROM, and on the left side is really the desired path. You come through a reset, this comes in, sets up a few of the processor registers. If you're familiar with the Spark, the trap-based register is one of your critical things to get that set right, and then processor status, and then basically walk through a couple of different initialization steps. And the most important thing is to checksum the next level, to do a check on the CRAM. Well, first it checks to see if the reset flag had said don't promote. If it didn't, then it'll go into the failsafe section. If the post is okay, if it's checksummed, it will then jump to it and again be done with it with this code. So again, this is the way we always hope to go. If for any reason we end up in here, we have a very small system that is designed to handle just critical operations. And there are, again, if you're familiar with the Spark implementation, you've got this huge trap table of possible traps. We only have to populate really 3 of them. In this case, we have the command handler, so we're ready to accept commands. At this point we want to be responsive to the requirements of the command and telemetry system on the spacecraft that we're working on. So we need to be able to take commands, we need to be able to provide telemetry. In this case, the only telemetry required and the only telemetry produced by this is either response to a command, and that response to a command, as you'll see later, is only going to be a read of a memory location, and then also a heartbeat status whenever probed by the higher level instrument, the higher level processor, because if we don't respond with that, it'll turn us off. Otherwise, we're looking for, if there are traps occurring that we aren't expecting, faults of some sort, we want to count them, we want to know what's going on. So we have some information as to what's going on in the system. But again, it's a very, very simple construction. To show you the difference, this is again now for our RBSP instrument, EMFISIS. Left side's identical, does the same thing. The right side, the only difference is that RBSP has this requirement for an instrument transfer frame. It's not quite as simple. All commands come bundled in a frame with a bunch of other commands and a bunch of other information, and all telemetry has to be bundled in this frame containing particular information. So it's a little more elaborate requirement to be able to produce this response appropriately. Also, on this experiment, we produce a mission critical piece of data for the navigation system. We produce the magnetic field data, and so even if we're in the AHBROM, they want us to make sure we're producing enough data so the navigation system gets magnetic field data to use for their spacecraft attitude determinations. And so again, we have to produce a little bit more. But again, that was all easy to do within the framework of the amount of space available here. The core reason for fail-safe or for this whole thing, again, is to make it simple and reliable. And simple is really the key, but flexible. And we can address any memory on the system. It's a memory map device, so we can really get to any interface, anything on the system. And we support our critical telemetry requirements. So in the case of MMS, we do the heartbeat status as required. On RBSP, we can receive the ITFs and provide the critical mag data. So again, the core of our system is commandability to us is critical. We don't ever want our system to not be commandable. And no matter what happens, what's failed, we still want to be able to get commands in and start probing and figuring out what happened and what we can do about it. So we've always used a non-maskable interrupt for getting our commands in. This is why we had to do a little bit of an extra step to prevent a command from coming in too soon in the boot process, because it is going to be responded to. But we do this minimal command set, and this is just meant to be a tool for rebuilding the system. It's not going to get any science out of this in this mode. This core is what we call a peek, poke, and jump. And that's really all it can do, but that's all it needs to do. You can read any address, you can write to any address, and once you've written to enough addresses, you can jump there. And that's, so the philosophy is you're not going to sit here and reload RTEMs from this. What you'll do, and what we have done many times, is you load a program that can load RTEMs, that can load the image. And you load that somewhere, and then you use that, you jump to that, and then you can build your capabilities quickly. It's just a typical bootloader, like, in some of the old days you had to do this by hand, toggling it in on the computer with the first few instructions. Well, this is really the same thing. You just build your way up. The command handler, for the fields one, they're very similar. Peek, poke, and jump, it would take a few liberties. We actually added a few extra commands, but they're all of the same flavor. We got really lazy on this one. We actually added a memory dump, so it's really a super peek. So we could actually get more than one response back at a time. A few other cases, there are certain registers that need special handling in the Leon to be able to read. You can't read them with a direct memory access, just a read. You have to do a little extra. So there was a critical devices addresses, so we added a couple of commands to do that. But the real core is just just these three, and and it's sufficient to operate the system. But there are a few things you have to keep in mind when you're working in this environment. You've got no stack, you've got no RAM, you've got no other device, so you can't do a return from interrupt. An interrupt occurs on the Spark, and it pushes return address on the stack. Well, that's fine. It just goes somewhere. We don't really care. But better not try and return to it. So, and when you return, so what we do in this case is every time a command comes in, anytime the basic core of the system is an idle loop. You're just looping around, waiting for something to happen. When a command comes in or any interrupt, you then process it, and then every command basically is like a new start. You reset all the parameters. So again, in the Spark environment, we reset the window manager. So we're only working in the first window of the Spark. We're not using all the resource available, but we're using what we need. And then there are a few registers available to hold pointers and configuration flags, so you can actually do multiple step commands. You don't forget everything on every start, but you can pass a few pieces of information along. The FPGA developer provided a few extra registers that are very helpful in the system to allow us to store some parameters that are preserved through a reset. So it gives us a little extra working space in the memory inside the FPGA. And just we've had a lot of experience with this now, and RBSP has been launched. It's on orbit now, and it's working. So far, we've only done the intended pass-through, other than our testing, where we force it, during a functional test, we always forced it into this AHBROM to make sure we can come back out again. MMS, so we've built the 2R CDPU boards in that same process I talked about earlier. On MMS, we've finished 3 of the 4 CDPU boards, again, through that same step. We've been testing and operating these things for years now. And this operates through the flight command and telemetry interface. So, and that's the way we've been using it. So all of it, and this is the way we program all of our flight software into all of our boards. There's no backdoor test interface, we don't use German to load the flight software. It all goes in through the command and telemetry interface through the same process. And in fact, just recently on MMS, we got to actually try it post-delivery. We had an issue with one of our CRAMs that we wanted to erase it and reprogram it. So we decided to take advantage of the AHBROM and start from scratch. So we actually cleared the entire CRAM device and we're able to go through with the AHBROM, load the program into RAM that allowed us to reload the CRAMs. And the nice thing about that, it was a really, really full, robust test of the system in the flight-like environment, something we wouldn't have really even asked to have the time and opportunity to do, something we do in our own lab all the time, but to actually get to do it, you know, on the instrument deck was actually a big plus and a big confidence booster. But the real key to our thing is to use this environment continuously through all of our integration and testing program so that we find all the little hidden features that we just hadn't thought about. So we're constantly testing them. I think that's the end. Yeah, any questions? Sure.
I have 2 questions. You said commands come in through a non-maskable interrupt. That means the hardware already does the decoding of the...
Yes. Yeah, the FPGA brings in the command string CCSDS packet in this case, in most of these cases, parses it either into a FIFO. If there are less than 2 words with the command, it'll put them in direct registers. If there's more than that, it puts them into a FIFO and then sends an interrupt to the processor.
The reality of decoding the command is completely hard and fixed in the system.
No, actually, it's just a string of, at this point, it's just a string of bytes come in, and the decoding of the command is done in the flight software. The only commands that are decoded by the hardware are, you know, the FPGA will look at the CCSDS header, pull out the opcode, and if it's, you know, one of 2 opcodes, it will then know what the next, you know, 32 bits contain, and it'll react to it. Other than that, it just passes it through.
And you said there was, I'm not sure which, RBSP, but the MAC data had to be,
Yeah.
The MAC data had to be provided to the spacecraft even while in boot mode.
Right.
Doesn't that violate your idea of not accessing any hardware on the outside the FPGA?
Oh, well, I mean, it's not, yeah, when I said the requirement on there was not to rely on on memory resources, SRAM, CRAM. In other words, we don't want to make any assumption about what code we have available to us. The hardware part, no, because we have to, you know, well, again, in this case, we're kind of stuck. You know, this is a requirement that we need to be able to provide this. So, and it is, in this case, there's no software involved in generating that data. The data is produced on power-on by the magnetometer, and the FPGA does the A to D acquisition capture. There's no software involved in creating that data. It's simply going and reading it from the device.